Sich for the y's. It seems like I could also have a cosh. Oh, see what I did there? Something sneaky. You could write cosh and sinh as an amplitude and a sinh plus a constant if you like. That's another way to write it. I found that convenient for the purposes of this problem, whatever. I think I was inspired by Ritger and Rose's excellent book to do this. But anyway, plugging in 1 is 0. That's the top. That's this one, right? And that tells me that the a sub n's, what do they have to do? Well, I have to have that n plus cn is 0. But that's only true, well, okay, so then putting that back in, I get y sub n of y is a sub n sinh of n times y minus 1. Okay, so that gives us this general formal solution like this. And then I need to fit phi of x0 equal to f of x, but when I plug in y equal to 0 here, that gives me minus 1, so I get sinh of minus n. So you see, it's not the Fourier decomposition of f of x. It's not the same. I mean, like the coefficients and the Fourier coefficients won't be directly the a sub n's, right? Because a sub n gets multiplied by this sinh of minus n. So what I'm going to have in this case is like the Fourier coefficients of this have to match a sub n times the sinh of minus n. But once I find the Fourier decomposition of f of x, then I can just kind of rip off from those I could assemble the solution from that. I think you can see that. Or not. Oh, okay, so let me see if I've got some solved over here. Yeah, here's one. Now, I said a two-dimensional Laplace equation, but Laplace's equation in general is just nabla squared u equal to 0. That can be like this in n dimensions, right? And so I've been looking at two-dimensional ones. You can solve three-dimensional Laplace problems just about the same way with just x, y, and z, rectangular. If you have like a rectangular, three-dimensional rectangular box-like region, it's pretty similar. I've solved those in junior level physics courses. They're not that bad. You might want to do that sort of thing if you want to understand the electrical properties of like a waveguide, which is essentially like a heating duct, right? But you send electrical waves through it. That would have electric and magnetic fields that are subject to boundary conditions because you got this like conductor, this running like that. And so, but the electric and magnetic fields are also described by this, the potential, the electric potential. Anyway, some of this math will eventually be used in electrical engineering to study waveguides, is what I'm saying. That said, in polar coordinates, you'd solve this wave equation. This is this Laplace equation. Here's the nabla squared in polar coordinates. Looks like that. Ugh. So, if you wanted to solve a problem in polar coordinates, it'd be a little different, right? For example, well, here's a full solution, by the way. Eventually, blah blah blah. Here's like a solution, a typical solution to one like I was just talking about. So if you look at practice homework 151 to 152, something like that, here's an explicit solution to a Laplace equation. This is from Nagel, Saff, and Snyder's book, which I recommend you study from. If you don't have a copy to look at, I can loan you one. Okay. I think I have a copy to loan. Anyway, sometimes it's hard to see where the answers in the back come from, but that's because there's a lot of tricky stuff that you can do with cinches and coshes in terms of identities. And like yeah. It will change the look of the answer considerably. All right, so what you'll see in my solutions is I'm reinventing the wheel again and again. Those first 4 propositions I have in chapter, I keep doing those again and again and again for specific examples. I finally decided at some point I should just present the boundary value problems, the standard fixed 0 endpoints, fixed derivative 0 endpoints, or mixed 0 endpoints as being standard things that I can refer to. If you look at the sum total of my work for the PDEs as you study the materials I posted, you'll notice that I'm not using those. What I'm doing is I keep going through the derivation of those problem after problem after problem, and I realized it was inefficient. But you do need to go through those a couple times until you should understand those propositions deeply before you use them. Anyway, so we'll solve the Dirichlet boundary value problem for the disk from 0 to 2. All right, subject to the boundary condition, f of theta is the absolute value of theta on minus pi to pi all the way around. So this one's kind of interesting because when you do the separation of variables, you get, okay, fine. You get minus t prime prime over t equals to k. That's fine. So the theta function, it's not too exotic. That's just a constant coefficient ODE. But the radial one, look at that. R squared, R prime prime plus R prime minus KR equal to 0. Do you recognize this? Do you remember what this is? What is this? Not constant coefficient. What if I had x squared y prime prime plus xy prime minus some constant times y equal to 0?
Looks like a small number.
No. What kind is it? We call these, this is a Cauchy-Euler problem. That's the Cauchy-Euler problem. So you see, when you have non-rectangular domains, the differential equations are more fun. Now you remember, yeah. So the equations are more fun. You end up with lovely things like this. Oh my goodness. So anyway, I have one solved there. I never cover this in the regular semester. Here's another polar problem with Neumann boundary value problem. Solution here to look at, enjoy. Another Dirichlet problem on an annulus. Periodicity of the theta function also comes into play here, which is some new feature. Didn't get to see that before. So there's some nice examples. What else do we have here? I'm almost done with this bit. I do have some PDFs posted with Fourier calculations. Let me see if I have one here. Yeah, here's a good example. Suppose you wanted to find the Fourier series for f of x equals x from minus pi to pi. Now, the problems we've looked at have all been from like 0 to pi, but there are other problems that go from, say, minus L to L. And so there the ball game's a little bit different. The Fourier decomposition can have both sines and cosines in it. Sometimes called the full Fourier. There's like the half. There's about 3 different popular Fourier decompositions. And you need all 3 to solve all the different problems that appear. They're related, but they're not the same. You just got to look at the book. I'm not going to try to explain that here, nor could I at the moment. I mean, I can explain, but it's not interesting to me at the moment. F of x equals to x on minus pi to pi. So it turns out, one of the differences is I had like a 2 over L. Now it's just 1 over.
Just
1 over L, where we're going from minus L to L, L being pi. Anyway, you do that, you get 0. The reason for that is because sine is odd, so it only needs sines in its Fourier expansion. And then here's the sines pick up a 2 over n times minus 1 to n plus 1. And so here's actually a picture of some of these. So basically we're saying the function x can be modeled by 2 times sine x minus sine of 2x plus 2/3 sine 3x minus 1/2 sine 4x plus 2/5 sine 5x minus 1/3 sine 6x, and so forth and so on. And here's like a graph just for the first 3. It looks something like this. If you go all the way to the first 6, it looks roughly like this. And then it'll keep repeating, though. It's not going to give you x. It's going to give you this kind of like triangular wave with this periodicity. If you go on, it does like this. And where it jumps, it'll always take the value of halfway in between. These series converge that way. The Fourier series, they will converge to the midway point between the jump. There's always some kind of discontinuity. Funny stuff happens at the jump points. Something called Gibbs discontinuity. or it's called the Gibbs effect. I'll show you. See if I find another one. Ah, no picture. No picture. Ah. Let's see here. Yeah, here's a good one. This is what I was talking about. So if you had, the question is, suppose you have a Fourier series for this f of x that's 1 from minus 2 to 0, and it's x from 0 to 2. So, like the value of the function, this is sort of the fundamental domain, if you like. The point of this problem in Nagel, Saff, and Snyder is just that the thing to learn is that when you calculate the Fourier series, it will actually converge to something. At the discontinuities, it converges to the halfway point. That's just from the theory of convergence of Fourier series, which I have not worked out to here. And we don't work out anywhere anymore in the math curriculum. Oh no. Why is that? That's a good question. I don't know. I guess students are more interested in taking courses on psychology of relationships and skiing on snowless mountains and stuff like that. I don't know. It's not just here though. It's just there's I guess there's a time and place for all math, and sometimes it gets old. Maybe that's it. I don't know. I have. This is a two-dimensional wave equation. You could also solve this with techniques like we've looked at. Oh, no, this is a two-dimensional heat equation. See, ut is uxx plus uyy. So that would describe the flow of heat. The flow of heat like a plate or something, a laminate, where you have a temperature given around an edge or something, and then how would it spread out after stuff like that. And so you can solve two-dimensional heat equations, which are interesting. You can also solve two-dimensional wave equations, which would be like a vibrating drum or something. You could do that. Dr. Skibordis has done that in the past. Not recently, I think. So that's it here. You can look at that. So the general game plan is just this. I will say this and then stop talking about these, but it's basically just this. You're given a partial differential equation with boundary values and or initial conditions. Sometimes you don't have initial conditions because there's no time.
Okay.
So, and then what you do is you separate variables. This brings you to ODEs, which are coupled in terms of some sort of characteristic value. You solve those ODEs subject to boundary conditions. That gives you some sort of formal solution which is built from a sum of all these boundary value solutions, all right? And then, typically, you fit the initial conditions to form the final solution. The fitting is done with the Fourier technique. Now, like I said, this needs modification if the boundary conditions are not of the simplest type. For example, you can look at that in Nagel, Saff, and Snyder. There's actually a lot more. If you look at an honest-to-goodness grown-up PDE book, the total algorithm for solving PDEs of this kind of variety is something like a 3-page process. It's like 15 steps. I don't know, my brother found it in some book. He's like, goodness gracious. I mean, I think these are probably about the longest undergraduate math problems you can find that are standardly assigned. I remember when I first took this course, I was working out my homework and I solved a problem and I looked back and I realized I had written 3 pages, 3 fairly dense pages, and I realized, wow, I really did something here. You really feel a sense of accomplishment when you finish one of these in its totality. And not just that, it's pretty cool what you're solving. You're describing how a string waves or how heat spreads out at something. It's really interesting, the physical implications of these things. Anyway, this is merely an introduction to PDEs. There's much, much more to learn in general. So, but this is a pretty decent, I think, standard introduction. Although what I have not done, which is a shame, is I have not motivated any of these PDEs physically. I would encourage anybody who is interested in the physical motivation for the heat equation, wave equation, whatever of these, Well, lots of standard books have decent explanations. I'm sure you could find something in Google. But if you're here, I think Dr. Skimbornis gives pretty decent derivations of wave equations and things in his DEs course. So even if I don't have them in my notes at the moment. Anyway, so you can cut it off, Bailey. Thank you, thank you.
So did I just let you describe waves?
Did you cut it off? Cut it off. Off. Off, I say.